Okay, so this is the first set of examples, and this is for 13.4, including that we're just starting to get into what thermodynamics is and so forth. Okay, so by now I think you should be comfortable with the idea, and you probably knew this from before you ever took physics, that when you heat something, it tends to expand. Not always, but it tends to expand because the molecules kind of spread out as the temperature increases, and hence it becomes less dense. As the temperature decreases, it becomes more dense. So we have that kind of thing. So this one is about how that precisely happens, and we have a nice law for what happens to the linear dimension of things and what happens to the volume dimension of things. Okay, so the first law that we have is the law of linear expansion. You know what? I shouldn't even call this a law. This is just an equation which works sometimes and sometimes it doesn't. But as long as you don't have an extreme temperature change, like really extreme, like maybe thousands of degrees, you should be able to look at this for linear expansion. Okay, so the change in the length of something is equal to this. That's all this equation says. So the original length, you should probably guess that's L0. 0 means initial or original. There's some kind of constant in there called alpha. That's just the constant of expansion, and it depends on the material. Let me bring up that page real fast. So in your book, you have a page of alpha coefficients. They're measured in this unit that's 1 over degrees Celsius for whatever reason to make the calculation come out in the right units. We could look at that, but I don't think we're going to. Anyway, so they gave you a bunch of those, and they've also given you a bunch of volumes. We might come back to that. Okay, change in L. Remember, this little triangle guy is always change, so that just means the final, like L final minus L initial. So notice, if we put this guy in for change in L, we'd have another initial temperature as well. So we could like do some factoring. I think in the book they substitute that in and go like, instead of saying LF, they say L minus L initial equals that stuff, and then they like solve it for L and combine some L0 terms so they get this. You can use whatever you like. This is just another option. That's just some basic algebra, so don't let it mess you up. Whew, I need to work on my drawing skills for today. Anyway, okay, let's look at an example with this. So let's pretend we have a bridge. I think this is a really nice example. It says you've got a bridge, and what happens when the bridge gets heated up so much, and what happens when the bridge gets decreased in temperature a whole lot. Like, what are you going to need to compensate for as an engineer? And this is a steel bridge, so we'll look at alpha steel, which is what? If we look at our table, steel, where is steel? Oh, iron ore steel, right here. So it's 12 times 10 to the negative sixth for that. Nice. So we say, okay, 12 times 10 to the negative sixth. Now precisely what's happening. They say the steel bed of a suspension bridge is 200 meters long at 20 degrees Celsius, so it's originally 200 meters. There's our initial length. And we've got an initial temperature, right? 20 degrees Celsius. If the extremes of temperature to which it might be exposed are negative 30 to 40 degrees Celsius, how much will it contract and expand? So let's look at the, I don't know, the 40 degrees Celsius. That's going to be 40. Change in temperature there is going to be final minus it starts out at 20. So that's 20 degrees. So what happens if we plug into our equation? We get the change in length. So how much is that bridge going to expand or contract? If it goes from 20 to 40, it's heating up, so that means it should expand, right? So this is an expansion. So we're going to go, just follow the formula. Easy stuff. Pretty important, though. I mean, engineers definitely have to take this into account, or a bridge could easily collapse. Initial length was 200. I'm just plugging in. And change in temperature we said is 20. Put that in our calculator. Let's see, how much does that bridge expand? I get 4.8 times 10 to the negative second, it's a length, so that's meters. If I don't put my units in there all along. Well, 10 to the negative second, so that's about how much? 4.8 centimeters. So that bridge is expanding that much. Now that might not seem like a lot, but if they make this bridge and don't account for that, then that could be a big problem, obviously. Okay, so what if it's negative 30? I think we'd have all this would be the same, except this one. I should put a subscript 1 there, subscript 2 here. I'm just going to say the same alpha, same 200 meters, and now we're going negative 30, whoa, minus 20, that's a negative 50 there, isn't it? So we put that in our calculator. So those two numbers times negative 50. Save yourself some work. So I get negative 12 times 10 to the negative 2. That's negative 12 centimeters. So negative 12 centimeters. That means it's contracting by 12 centimeters when it's that cold. That's quite a bit. I mean, that's like, what, almost a foot? I don't know, half a foot, something like that. That's a lot, so they've got to be careful. So those, whatever they do with the bridge, when they make the joints at the edges of the bridge, they've got to make them that flexible so that they can go back and forth. How many centimeters is that total? About 17? About 17 centimeters of play in the bridge joints. Okay, let's look at another one. This is really 2, but the book treats it as 2. I think it's really the same problem. So first of all, the question is, what if you have 2 pieces of iron like this? Let's see what I mean. I mean like a piece of iron that's this, a ring, basically just like a washer. If you've got some kind of washer that you put on a bolt, very, very common, right? And this one we're going to think of as all colored in. Okay, the question is, if you heat this washer, what's going to happen? Does the hole get larger or smaller? So I think that if we all think about it, we're all going to say, yeah, those red lines are going to expand. And now a lot of us, I think, are going to think in this first one that, like, as they expand, these also expand. It expands this way as well toward the inside. And therefore it's going to shrink. But that's really not the answer, so this is a little bit counterintuitive. When the metal actually expands, the material inside doesn't do that. The material inside is also going to expand in an outward fashion. So the washer is going to increase in size. And I think if you think about maybe something you've seen in the movies or personal experience, a lot of the time when you're trying to get something loose, what do? When you're trying to loosen something up, most of the time, especially if it's on a metal surface, if you're working with an engine or anything like that, when you try to loosen something up, what do? Do you heat it up or cool it down? You heat it up, and that makes sense. When you heat something up, the metal and all other materials not as much, but they expand as well. And that's kind of what happens. So this situation does make sense with experience. I'm just getting out of control today with these drawings. Holy moly! Let's make a nice clear thing. So nope, it does this, right? Inside and outside expand. Okay, so let's say we have a ring on a rod. So we've got like a washer around a rod like this. And we want to know something. So let's look at the specifics. It says an iron ring is to fit snugly on a cylindrical iron rod. At 20 degrees Celsius, the diameter of the rod is 6.445 centimeters, and the inside diameter of the ring is 6.420 centimeters. I'd read along in your book if you can. To slip over the rod, the ring must also be an extra amount bigger so that it has some extra space by about 0.008. It says to what temperature, how much do you have to heat the rod before you can put that washer over it so it slips over it. Okay, so once again, we've got this. They're asking about temperature, so I solve for delta T, and I think I'm just going to plug in my numbers. So we're going to say this is iron, so I think we had that number from before. Wasn't it 12 times 10 to the negative 6th for either iron or steel? I'm sure it's a little different, but we're going to use that for both. What was the initial length that we had? Well, the initial length, I think, is the inside diameter of the ring. So that's going to be 6.420 centimeters. I could put that in scientific notation by going times 10 to the negative 2. I'm just going to leave it all in centimeters here. Okay. Okay, so what about the change in length? Well, what is the final length that we want? Isn't the final length we want the rod plus the space? Yeah, so that's 6.445. So let's look at it over here. Change in L is going to be like L final minus L initial. Okay, we already know what L initial is. That's just the diameter of the ring, so we can put that in. So minus 6.420. We had that down here too. Okay, so the final one is that we want is the rod plus the space we need, remember? So that's going to be, what, 6.445, and we also need that little bit of space. Just a little bit. Oh my goodness, cat. So that's L final minus L initial, which I already put up there. So what is this right here? I think that's 6.453, and then we'll get an answer. So how much does this rod and washer need to be heated up? That's 430 degrees. But remember, they said it was already at 20 degrees. This is the change in temperature. So I think we need to heat it up not 430 degrees. We need to take it 430 plus what we've already got, which is 20. So plus 20 is 450 degrees Celsius. So we might use a blowtorch or a acetylene torch or something like that to do that. Okay. Let's look at one last example here. And before we do that, I thought we looked at linear expansion when you heat something up. Now let's look at volume expansion or contraction when you heat or cool something. So it apparently goes by just about the same law. If you look at our table back here, erase all that stuff. Notice it has linear coefficients and volume coefficients, and they're in the same units. For most solids, especially metals, they're about 3 times bigger. You can see that the aluminum, linear, and volume are about 3 times bigger. That's just the kind of the law it follows. You want to be careful with that. The other thing I want to be careful about is why is there this big hole right here in the table? Well, think about it. These are all solid examples, and these are liquids. And then if we scroll down a little bit, we can see some gas. They just have air. Why don't they have coefficients? They have volume coefficients for those, and they're much larger if you look. But why is there no coefficient for linear expansion? Well, because solids and liquids don't have a linear shape, right? They can fill a volume. You can put them in a container and measure their volume. But how do you measure their length? You can't measure the length of something that's solid. Of something that's a liquid or gas. So I just thought we'd talk about that. Obvious, but you don't want to think about it. You get confused. Anyway, this last problem is kind of neat. It says, what if you have a car in the sun and you heat it up? What happens to the gas in the tank and so forth? So what happens? So it says there's a 70-liter steel gas tank. So what is that? 70 liters, isn't that an initial volume? So let's put that in as an initial volume. 70 liters. Okay. The steel gas tank, so we get beta for steel, which is 35 times 10 to the 6th. Excuse me. And I think we also want to look at for gasoline, so let's put that's steel. Let's put this one as gas. What is it for gas? 950 times 10 to the negative 6th. This was 35. I don't know. Whatever. Okay, so we're going to do 2 separate problems. We'll look at the gas expansion, and we'll look at the tank expansion as it heats up. Okay? So the temperature we're going to say goes from, it says the car starts out at 20 degrees, and it goes up to 40 degrees Celsius. So 40 minus 20, that's 20 degrees Celsius change. Okay, so let's look at gas first. So if we look at the gasoline, we plug in the gas constant, which was 950. And then it says multiply by the initial volume, which was 70. We'll just leave everything in liters. And then we had a 20-degree change in temperature. So what do we get? That's about 1.3 liters. So apparently there's that much more gas volume as it heats up. So that's kind of crazy. I hope our gas tank can accommodate that. A little skeptical. So 36 times 10 to the negative 6. The other numbers are the same, of course. Put that in our calculator, and it is a lot less. So notice the gas expands a lot, the tank expands just a little bit, you're going to lose some gas. So something you might think about, this is especially like if you're going to the gas station and you're filling up like some gas cans for your lawnmower, for whatever other machines that you have around, like a generator or something. You always want to fill them less than putting it to the top, because if you leave them out in the sun, as is definitely possible around here, it's going to have the gas expand a lot. And a lot of the time the container, even if it's a plastic container, can't handle that and you'll lose gas. Or it can even explode in some cases. You never want to fill them to the tops. You know, same thing with your car gas tank maybe. Another thing the book says is I really like theirs. It says, want to save a few pennies? This could be dollars. I mean, geez, if it's that much money for a liter of gas, and it is. Fill your gas tank when it's cool. So apparently in the winter you pay less for gas because the gas is more dense when it's cool, just like everything else. Okay, that's it for this video.